Hello everyone. So this is the second hour of magnetism and matter. And in this hour, we are going to talk about tangent galvanometer, moving coil galvanometers. Then we are going to talk about magnetic properties of substances like paramagnetic material, diamagnetic material, ferromagnetic material. So let's start today's hour with the first agenda, that is tangent galvanometer. So how does a tangent galvanometer works and why it's called tangent galvanometer? First of all, you need to understand in the tangent galvanometer, we have a magnetic needle which is free to rotate in the horizontal plane. If you have a magnetic needle which is free to rotate in the horizontal plane, in which direction it will point? Sir, a magnetic needle which is free to rotate in the horizontal plane will point in the direction of horizontal component of Earth's magnetic field, in whichever direction it is. And this small magnetic needle which is mounted over a horizontal plane so that it can rotate in the horizontal plane is placed at the center of a big coil. Now this coil can be turned about a vertical axis passing through its center. So this coil is vertical and it can be turned around a vertical axis passing through its center, something like this. So now how do we use a tangent galvanometer? So let the needle come into equilibrium without driving any current in the coil. So first, do not drive any current in the coil and let the magnetic needle come into equilibrium. It settles in the direction of horizontal component of Earth's magnetic field. So in whichever direction this needle settles, that is the direction of horizontal component of Earth's magnetic field. Now the next point is important. Then we turn this coil about its vertical axis and make sure that the needle lie in the plane of the coil. So if let's say needle point towards west, then we turn the coil such that the needle lies in the plane of the coil. If let's say the needle points in the northeast direction, then we turn the coil about the vertical axis such that the coil contains the needle. Turn the coil so that the needle is in the plane of the coil. Why do we do so? Because now the field produced by the coil is normal to its plane. The field produced by a current carrying coil is normal to its plane, and we know that this field strength will be nothing but N times mu naught I by 2R, where N is the number of turns in the coil, mu naught is permeability of free space, I is the current flowing through it, and R is the radius of the coil. So now the field produced by the coil is normal to its plane and perpendicular to the Earth's magnetic field. You first let the needle settle, yes. In whichever direction the needle points, that's the direction of Earth's magnetic field, right sir? Now you turn the coil so that the plane of the coil contains the needle, okay? Now when you drive some current in this coil, it produces a magnetic field perpendicular to its plane, which is nothing but perpendicular to direction of Earth's magnetic field. Now we know that once the coil will produce a magnetic field of its own, the needle will budge, and now the needle will point in the direction of net magnetic field. Why? Because a freely suspended needle points in the direction of net magnetic field. So on driving current, the needle deflects in the direction of net magnetic field. Net magnetic field because of what? Both due to Earth as well as due to the coil. So let's say first the needle set in a particular direction, and that direction will be the direction of horizontal component of Earth's magnetic field. Once you drive the current in the coil, it will produce a magnetic field perpendicular to the plane of the coil. Hence, it will produce a magnetic field perpendicular to the horizontal component of Earth's magnetic field. And let's say this magnetic field produced by the coil is magnetic field due to the coil. Now the needle will deflect and point in the direction of net magnetic field in its plane. And the net magnetic field in its plane will be the resultant of magnetic field produced due to the coil and the magnetic field due to horizontal component of Earth's magnetic field. So let's say the net magnetic field come out to be somewhere here. You will say that initially the needle was pointing in the direction of horizontal component of Earth's magnetic field. Once you drive some current in the coil will produce a magnetic field of its own, and now the needle will point in the new direction of net magnetic field in its own plane somewhere here. So the needle deflects by some angle theta, and this deflection shown by the needle theta can be found using tan theta equals to the magnetic field produced by the coil upon the horizontal component of Earth's magnetic field. So tan theta will be equals to magnetic field produced by the coil upon the horizontal component of Earth's magnetic field. You can rewrite the magnetic field produced by the coil as number of turns in the coil times the magnetic field produced by one turn, and the magnetic field produced by one turn will be nothing but mu naught I by 2r. So in place of magnetic field produced by the coil, you can write n mu naught I by 2r upon ph. Now you can bring this 2r to the denominator and you will get tan theta equals to mu naught and I upon 2r ph. So now let's think of, we have got that tan theta equals to mu naught and I upon 2r ph. Yes sir. We can see here the current flowing in the coil is directly proportional to tan theta. For our moving coil galvanometers, the current flowing in the coil is directly proportional to the deflection shown by the needle theta. But in case of tangent galvanometer, the current flowing in the coil is directly proportional to tan theta. That's why the name tangent galvanometer, and the full form of the term tan is nothing but tangent. So we know that I equals to, bring this 2 up, r up, bh up, mu naught down, n down. So you will get I equals to 2 r bh upon mu naught n into tan theta. Or you can say that the current in the coil is directly proportional to tan theta. So this is the standard question that gets asked. If the angle of deflection of the needle in a tangent galvanometer changes from 30 degree to 60 degree, the current becomes how many times? So you will say that, let's say initial current is I1 and the final current is I2. We know that for a tangent galvanometer, I is proportional to tan theta. Let's take the proportionality constant as K and write I equals to K tan theta. So we can write I1 equals to K tan 30 degree, I2 equals to K tan 60 degree. And we know that tan 30 degree is nothing but 1 by root 3. So here you get K by root 3. And tan 60 degree is root 3. So here you get root 3K. So you can say that I1 by I2 equals to K by root 3 upon root 3K. That becomes 1 by 3. This means that I2 is 3 times of I1. This means that for the deflection in the tangent galvanometer to change from 30 degree to 60 degree, the current in the coil must become 3 times, and this is a standard question that gets asked. So beta, remember that. So if the angle in tangent galvanometer changes from 30 degree to 60 degree, here the current is not at all proportional to theta, that is in our moving coil galvanometer. Here the current is proportional to tan theta. That's why the name tangent galvanometer. So if the angle changes from 30 degree to 60 degree, it means that the current become 3 times. Now let's move on and talk about our moving coil galvanometer. So the normal galvanometers that we use in the lab. Inside the normal galvanometers that we use in the lab, we have got concave permanent magnets, and we have got this cylindrical region between them which is empty. So looking from top, here you can see a north pole, here you can see a south pole, and there is a cylindrical region present between them which is empty. Why do we use these types of magnets? It's important. Let's see. So here we have got a permanent north and a permanent south, and in the region between them there is a cylindrical void where we are going to place the coil. We use these type of concave magnets so that we can get radial magnetic field in the region between the two poles. Now bachon, inside a galvanometer we use concave magnets, right? Why do we use concave permanent magnets? So that the magnetic field in the region between them is radial in nature. Sir, why do you need a radial magnetic field? So that the torque acting on a current carrying coil is independent of its orientation. Sir, I did not get it. We'll explain. Keep focusing. Let's say you have placed a current carrying coil in the cylindrical region, in the cylindrical empty region between the two poles. Now, the force acting at the wire of this current carrying coil will be due to the magnetic field line in its own plane. There will be no force on these current carrying wires of the coil due to the magnetic field at some angle to it. That's why we use the radial magnetic field, so that the field which is applying the torque on the current carrying coil is the field which lies in its own plane. So we keep the magnetic field lines radial so that the torque on the loop is independent of orientation. Keeping radial magnetic field lines, we ensure that irrespective of the orientation of the current carrying coil, the magnetic field which applies the torque on the coil is the one which lies in the plane of the coil. Now, when the coil, let's say faces like this, the magnetic field which applies the torque is the one which is present in its own plane. Now, bachcho, when current flows through the coil, we know that a magnetic torque will act on the coil. And this magnetic torque can be calculated using torque equals to M cross P. Since the torque is being applied by the magnetic field which is in the plane of coil, and the magnetic moment of a coil is perpendicular to plane of coil. Hence, the angle between magnetic moment of the coil and the magnetic field which is applying the torque is 90 degree. So you can write the torque magnetic to be nothing but the magnetic moment of the coil multiplied by the strength of the radial magnetic field. Now, bachcho, once you place it between these concave permanent magnets and drive some current, it will start rotating continuously due to the torque of the radial magnetic field if there will be no restoring torque. And the restoring torque here is provided by the spring placed under the coil. So, sir, is this how the motor works? Yes. A motor is nothing but a coil placed in a radial magnetic field in which you drive the current, and if there is no one to provide the restoring torque, the coil keeps on rotating, and that gives us a motor. Now, here we place a spring, and as the magnetic field applies the torque, the spring twists, and the twist in the spring provides the restoring torque. At equilibrium, the torque provided by the magnetic field is exactly balanced by the restoring torque provided by the twist in the spring. So we say that the spring provides the restoring torque that does not let the coil keep on going over and over and over again like a motor. Now we know that the torque magnetic will be nothing but MB, because the angle between the magnetic moment and magnetic field will be 90 degree, as the magnetic field which is applying the torque lies in the plane of the coil and the magnetic moment has to be perpendicular to the plane of the coil. So using the torque equals to M cross B, we can write the magnitude of torque to be equals to magnitude of magnetic moment times the magnitude of magnetic field times the sine of angle between them, and sine 90 becomes 1. That's why you get the magnetic torque to be MP. You can write in place of magnetic moment the number of turns in the coil times the current flowing through the coil times the magnitude of the area of the coil. If the coil is a circle of radius r, then the area will be written as pi r square. So NIAB, this is the magnetic torque acting on the coil. The restoring torque provided by the spring is nothing but the torsional constant multiplied by the angle twist at theta. So restoring torque provided by the spring is directly proportional to the twist in the spring. So the restoring torque is nothing but C theta. Now, further talking about galvanometer. Let's say the needle of the galvanometer comes to equilibrium after turning through an angle theta. At equilibrium, the torque acting on the coil due to the magnetic field is balanced by the restoring torque provided by the twist in the spring. So you can say that the torque magnetic equals to torque by the spring at equilibrium. The torque by the magnetic force is nothing but NIAB, and the torque provided by spring equals to C theta. Hence, bachcho, you can write theta equals to nothing but NAB by C times I. Now, bachcho, you can see here for a galvanometer, a moving coil galvanometer in which the coil turns, the deviation produced is directly proportional to current. So if for this galvanometer they say that the deflection changes from 30 degree to 60 degree, you will say that, sir, the deflection becomes double. And for the deflection to become double, the current in the coil should become double. In tangent galvanometer, we got that the current should become triple. Now here we will coin two terms. The first one is called current sensitivity. What is the meaning of current sensitivity? How sensitively the device measures the current. The current sensitivity of a galvanometer is represented by the deflection in the needle upon the current flowing through it. So current sensitivity is defined as theta upon I, the deflection shown by the needle upon the current flowing through the galvanometer. Theta by I represents current sensitivity, and to find it you just bring the I here and you will say that current sensitivity is nothing but NAB by C. So as to make a galvanometer more current sensitive, you should increase the number of turns in the coil, you should increase the area of the coil, you should increase the strength of the magnets, or you should replace the spring with another spring of lower torsional constant. But sir, what is the physical significance of current sensitivity? Visualize two galvanometers, the first galvanometer and the second galvanometer. In both the galvanometers, you let's say drive the same amount of current of let's say 2 ampere and 2 ampere. Let's say in the first galvanometer, the needle deflects by an angle of 10 degree. While in case of second galvanometer, for same current, the needle deflects by an angle of 30 degree. So which galvanometer you will say to be more sensitive? Sir, a person is said to be more sensitive when they show more output for the same input. If I crack the same joke on two friends and one of them get very angry, we will say that that friend is very sensitive. Similarly here, we can see that on driving the same current in the second galvanometer, the deviation is 3 times. The angle of deflection is 3 times. So you will say that the second galvanometer is 3 times more sensitive for current than the first galvanometer. So the current sensitivity is defined as theta by I. To make a galvanometer more current sensitive, increase the number of turns or increase the area or use stronger magnets so you have got higher magnetic field, or replace the spring with another spring of lower spring constant. Now we will talk about another term which is called voltage sensitivity. Just like current sensitivity is the deflection shown upon the current flowing, voltage sensitivity is nothing but the deflection shown upon the applied potential drop. So if you have a galvanometer 1 and another galvanometer 2, you apply the same potential drop across them, let's say 10 volt, and on applying the same potential drop, if the deviation in the first galvanometer is 20 degree and the deviation in second galvanometer is 30 degree, you will say that the second galvanometer is more voltage sensitive, because on applying the same potential drop, it shows more deflection. So the greater the theta for a given potential drop, the more voltage sensitive the device is. Now how to find the voltage sensitivity? We are going to use the same old potential drop equals to IR. From here kids, you can write theta by I equals to NAB by C. Yes sir, you have already written it. If we divide both the side with the resistance of the coil, and I can write this IR as the potential drop across the coil. So we will say that theta upon V is nothing but NAB by CR. So in place of V you can write IR, and theta by IR is same as NAB by CR. What is R? Resistance of the coil placed inside the galvanometer. Now how to increase the voltage sensitivity? Increasing the number of turns? No. Why? Because when you increase the number of turns of the coil, you also end up increasing the resistance of the coil. Do understand that the voltage sensitivity theta by V is nothing but NAB by CR. Increasing the number of turns in the coil, you increase the resistance by the same factor. If you make the number of turns in the coil double, then the length of the coil used becomes double, and hence the resistance of the coil becomes double, so it has got no impact on the voltage sensitivity. If the number of turns becomes triple, then the resistance of the coil becomes 3 times, and again the voltage sensitivity ends up being the same. So to understand that voltage sensitivity can't be changed by changing the number of turns. No doubt if you increase the area of the coil without changing the resistance somehow, then the voltage sensitivity increases, or if you replace the magnets with stronger magnets, the voltage sensitivity increases, or if you replace the spring with another spring of lower spring constant, of lower torsional constant, then the voltage sensitivity increases. So you need to remember that we can't increase voltage sensitivity by increasing the number of turns, as it also increases the resistance of the coil by the same factor. So now we will talk about the magnetic properties of substance: ferromagnetic, diamagnetic, paramagnetic. But before we do it, we need to understand how do we magnetize a substance and what are the terminologies related with it. In the old times, when we did not had electricity, to convert an iron block into magnet, this method was followed. We will take a piece of iron, we will heat it up till it starts glowing, till it becomes red hot. Then we will align it in Earth's north-south direction. Why? Because Earth has got a magnetic field of its own towards the north. And as this hot iron got cooled down slowly in the presence of Earth's magnetic field, it gets magnetized and it converts into a magnet. But these type of magnets created were not strong enough. Why? Because the Earth magnetic field is not a very strong magnetic field. So we need to understand some terms related to magnetizing a substance. The first term I am focusing on is magnetizing field intensity. The symbol used is H. Magnetizing field intensity. The field which is trying to magnetize the substance. When you place the iron block into the Earth's magnetic field, the field which is trying to magnetize the substance is the Earth's magnetic field. So magnetizing field intensity represents the field intensity which is trying to magnetize the substance. But sir, why you have used a different symbol from magnetic field? Because it's a different quantity. First of all, understand that a magnetic field applied to magnetize the material is called magnetizing field intensity. Now, by the mathematical definition, we say that the magnetizing field intensity is nothing but the applied magnetic field, the magnetic field placed to magnetize the substance, divided by permeability of free space. So, what is the magnetizing field intensity? The applied magnetic field to magnetize the substance divided by mu naught. But nowadays we have devices that can produce a strong magnetic field. Nowadays, to magnetize a substance we use solenoid. So to magnetize a substance we place it inside a solenoid. Why? Because we know that when we have a solenoid and there is a current I flowing through it, by increasing the magnitude of current we can increase the strength of magnetic field within the solenoid, and the strength of magnetic field within the solenoid is given by mu naught and I. So you can create as strong magnetic field as you want by just increasing the current in the solenoid. Now question is, if a current I flows through the solenoid, what is the magnetizing field intensity inside the solenoid? And it's a simple thing. Magnetizing field intensity is nothing but the applied magnetic field to magnetize a substance divided by mu naught. So we know that H equals to B by mu naught, and the magnetic field inside a solenoid can be written as mu naught Ni. So you will write the magnetizing field intensity, the external magnetic field which is trying to magnetize the substance, is nothing but mu naught Ni divided by mu naught, and cancelling out mu naught, you get that the magnetizing field intensity inside a solenoid when a current I flows through it is nothing but Ni, where N is the number of turns in the solenoid per unit length. Now the second terminology that we need to understand is called intensity of magnetization. When you place the iron block after heating into the Earth's magnetic field, we know that when it cools down slowly, it gets magnetized. But what is the meaning of it gets magnetized? It develops a magnetic moment of its own. It starts acting like a paramagnet. We define another quantity called intensity of magnetization. And this quantity, intensity of magnetization, represents how much the substance has magnetized, how strongly the substance has converted into a bar magnet. So we determine this quantity I as when a substance is magnetized, it develops a magnetic moment. Yes. We say that the intensity of magnetization is nothing but the magnetic moment developed in the substance per unit volume. So if you place the iron after heating into Earth's magnetic field, the more the magnetic moment it develops, you say that the more is the intensity of magnetization. Intensity of magnetization, how much the substance has been magnetized. Magnetizing field intensity, how strong is the field which is trying to magnetize the substance. So you need to understand these two terms clearly. So intensity of magnetization is nothing but the magnetic moment developed in the substance per unit volume of the substance. Now, if we have a bar magnet, and we know that if we have a bar magnet of cross-sectional area A, then the magnetic pole strength of the bar magnet is directly proportional to the cross-sectional area. The greater the cross-sectional area, the higher is the magnetic pole strength, right? Now, we say that the intensity of magnetization, how much a substance has been magnetized, is nothing but the magnetic moment of the substance divided by its volume. For this bar magnet, you will say that the intensity of magnetization is its magnetic moment divided by its volume. The magnetic moment of this bar magnet will be nothing but the pole strength times the separation between the poles, which is M times L, upon the volume of the bar magnet, which is nothing but the cross-sectional area into length. So you can write this as, in place of magnetic moment, the pole strength into length, and in place of volume, you can write the cross-sectional area times length, and you can cancel out the length and length. So you get that the intensity of magnetization for a bar magnet is nothing but the pole strength divided by the cross-sectional area. Or you can see why I said that the pole strength is directly proportional to the cross-sectional area. So the greater the cross-sectional area, the greater is the pole strength. So now let's talk about the quantity which correlates the magnetizing field intensity and the intensity of magnetization, and this quantity is called magnetic susceptibility. If let's say we have placed a material in an external magnetic field, this external magnetic field tries to magnetize the substance. Now the intensity of magnetization is directly proportional to the magnetizing field intensity. To make you understand this, think of that iron block placed in Earth's magnetic field after heating. It will magnetize, it will develop some magnetic moment per unit volume. But if you place the same iron block after heating inside a solenoid in which you drive huge amount of current, so there will be way stronger magnetic field. And because of this way stronger magnetic field, the substance will magnetize more. So the intensity of magnetization, how much the substance will magnetize, is directly proportional to the magnetizing field intensity. Now every time a physicist finds a proportionality, they add up a proportionality constant, and we say that the intensity of magnetization is nothing but susceptibility times the magnetizing field intensity. So I equals to psi h. Now let's say you have taken a piece of iron, okay? You have placed it in a strong external magnetic field. This iron block also gets magnetized. It develops a pole of its own. So you will find here a north, here a south. Now, once it develops a magnetic moment of its own, you know that there will be a magnetic field inside the substance due to the magnetic moment of its own. We know that outside a magnet, it produces the magnetic field from north to south. But inside the magnet, it produces a magnetic field from south to north. So within this magnetized substance, now there will be two types of magnetic field. One due to external, another due to the magnetization of the substance. Since this material has now developed a magnetic moment, it will also produce a magnetic field within itself in the direction of its magnetic moment. And you can say that now the net magnetic field inside the substance once placed in an external magnetic field will be equal to the applied magnetic field, which is the external magnetic field, plus the magnetic field due to the magnetic moment developed in this substance. In place of applied magnetic field, we can simply write mu naught times the magnetizing field intensity, because that's the relationship. Magnetizing field intensity is nothing but the applied magnetic field divided by mu naught. And in place of the magnetic field, due to the magnetic moment developed, we can write mu naught times the intensity of magnetization. Now this is something new which we haven't learned till now. So you will say that the net magnetic field inside equals to mu naught h, this we have learned already, plus mu naught I. The magnetic field produced inside a material due to the development of magnetic moment is nothing but mu naught I. This is something I am telling you for the first time, and most of the students do not know this, so keep this in mind. Now, in place of intensity of magnetization, you can write susceptibility times the magnetizing field intensity. So here, on substituting, you will get mu naught h plus mu naught psi h. Now you can take mu naught h as common, so you will get the net magnetic field inside equals to 1 plus psi times mu naught h, and in place of mu naught h, you can write the applied magnetic field. So the net magnetic field inside the material equals to 1 plus susceptibility times the applied magnetic field. We have learned while learning electric field that the electric field inside the material equals to the electric field applied upon dielectric constant. And I said that dielectric constant and relative permittivity are synonyms. So we can write the electric field inside equals to applied electric field upon the relative permittivity. Similarly, beta, we say that the net magnetic field inside equals to mu r times the magnetic field applied. Sir, from where do we get this? How to remember? Remember that in all the formulas of electricity, you always find 1 by 4 pi epsilon naught. Epsilon naught is in the denominator. And in all the formula of magnetism, you find mu naught by 4 pi. Mu naught is in the numerator. The same type of thing happens here as well. The net electric field inside equals to applied electric field divided by the relative permittivity. The net magnetic field inside equals to magnetic field applied multiplied by relative permeability. So one can even say that the net magnetic field inside equals to relative permeability times the applied magnetic field. And now comparing these two, you can say that, okay, 1 plus susceptibility is nothing but the relative permeability. So one can say that relative permeability of material is nothing but 1 plus susceptibility, and you need to remember this result. So if the relative permeability is 5, it means that susceptibility is 4. If the relative permeability is 6, it means that the susceptibility is 5. So relative permeability is nothing but 1 plus susceptibility. And what is the susceptibility? Susceptibility is the ratio of intensity of magnetization, how much the substance has magnetized, divided by the magnetizing field intensity, the field that has been applied to magnetize the substance. Now, bachon, we will talk about the types of materials. There is something called paramagnetic material, there is something called diamagnetic material, there is something called ferromagnetic material. And what is the basic difference between these three types of material? Paramagnetic materials are the one which are feebly attracted towards the magnetic field. In chemistry, you have learned that paramagnetic materials are the one which have got unpaired electrons. Since they have got unpaired electrons, the molecules of the paramagnetic materials have a magnetic moment of its own. So, paramagnetic materials have molecules with unpaired electrons, yes. Hence, each molecule has some magnetic moment. When we talk about diamagnetic substances, the molecules of the diamagnetic substance have paired electrons. Hence, each molecule have got no magnetic moment. And you can think of ferromagnetic materials to be the extreme case of paramagnetism. So, think of ferromagnetism as extreme case of paramagnetism. Keep this thing side for a while. Let's first talk about paramagnetic and diamagnetic. Then I will explain you why one should think of ferromagnetism as extreme case of paramagnetism. So first of all, let's talk about paramagnetic substances. What are paramagnetic materials? In paramagnetic materials, each molecule have individual magnetic dipole moment, as each molecule have got unpaired electrons. Now, if we have a crystal of paramagnetic material, then each and every molecule will have magnetic dipole moment of its own. but magnetic dipole moment is a vector quantity. So if I ask you, if you have a paramagnetic material, do every molecule have a magnetic dipole moment? You will say yes, and hence the magnetic dipole moment is non-zero. But if I give you a crystal of paramagnetic material and ask you, does this material have a net magnetic dipole moment? You will say, sir, magnetic dipole moment is a vector quantity. All these magnetic dipole moments point in random direction and they end up cancelling out each other. So the magnetic moment of the material in the absence of external magnetic field comes out to be equals to 0. The material do not have a net magnetic moment. Each and every molecule have some net magnetic moment. Now let's say we place this paramagnetic substance in an external magnetic field. We have learned that a freely suspended dipole always try to align in the direction of field. So due to the applied magnetic field, these magnetic dipoles will start aligning in the direction of magnetic field. So some of the dipoles will be successful in aligning in direction of field, as you can see. The stronger the field you will apply, the more the number of dipoles will align. Sir, my doubt is here, what? Why not all the dipoles align? Still I can find many dipoles which are not in the direction of applied magnetic field. Better, this is due to thermal agitation. The molecules which we think are at rest are actually continuously vibrating. Now due to the thermal agitation, it is impossible to make all the dipoles align in the direction of magnetic field for a paramagnetic substance. Now once you have placed the paramagnetic substance in an external magnetic field, since the magnetic dipole align in the direction of field, the substance gets now a net magnetic moment in the direction of field. Now since the substance now have a net magnetic moment in the direction of field, within itself it will now produce a magnetic field of its own in the direction of applied magnetic field. So bachcho, now the magnetic moment of one molecule is still non-zero. It's paramagnetic substance. But once placed in an external magnetic field, the material also develops a magnetic moment and the magnetic moment of material is also non-zero. Now bachcho, the stronger the applied field, the stronger the applied magnetic field, the better the alignment. Second point, all molecules do not align due to thermal agitation. So if you heat up the crystal, there will be more thermal agitation and the alignment will be worse. The next point is, they are feebly attracted by magnetic field. Paramagnetic substances are feebly attracted by magnetic field and move from the region of weaker magnetic field to stronger magnetic field. So let's say if you have a bar magnet. Question is, paramagnetic substance is attracted towards the north pole of bar magnet or towards the south pole? The paramagnetic substance is attracted towards the bar magnet. Towards which pole? Both the poles. Do understand that paramagnetic substances like to move from the region of weaker magnetic field to stronger magnetic field. Outside a bar magnet, we find that the magnetic field lines are from north to south. Yes, sir. So nearby the pole, the field lines are closer. Yes. So the field strength is higher. Yes. So whether you release a paramagnetic substance here, it will try to move from the region of weaker magnetic field to the stronger magnetic field. Or whether you release the paramagnetic substance here, it will try to move from region of weaker magnetic field to stronger magnetic field that is closer to a bar magnet. So you need to understand that paramagnetic substances are feebly attracted by magnetic field, not like the way a magnet attracts an iron, and move from region of weaker magnetic field to stronger magnetic field. Now we need to talk more about the paramagnetic substances. When you have placed a paramagnetic substance in an external magnetic field, we know that the substance develops a magnetic moment in the direction of applied magnetic field. And this magnetic moment is directly proportional to the applied magnetic field. Stronger the applied magnetic field, better the alignment, more is the magnetic moment developed within this crystal. Now if we think of the graph of intensity of magnetization versus magnetizing field intensity, For a paramagnetic substance, the graph goes like a straight line because we have already learned that the intensity of magnetization is directly proportional to the magnetizing field intensity, and we get this type of graph. The slope of this graph, let's say this angle is theta, then tan theta gives you I by h, and I by h is nothing but the susceptibility. So remember that the slope of this IH graph gives you the susceptibility of the paramagnetic substance. Understand that the susceptibility of paramagnetic substance is a small positive number. The paramagnetic substances do not have very large susceptibility. They are feebly attracted by magnetic field. So the susceptibility of paramagnetic substance is a small positive number. And mu r is greater than 1. We know that mu r equals to 1 plus psi. Yes. If psi will be a small positive number, then the relative permeability has to be greater than 1. So the relative permeability of a paramagnetic substance comes out to be greater than 1. Do understand that the net magnetic field inside is greater than the applied magnetic field for the case of paramagnetic substance. On increasing the temperature, the susceptibility of a paramagnetic substance decreases. Why? If you heat it up, the thermal agitation will increase. The thermal agitation will increase, so the alignment of molecules in the direction of field will be weaker. So the magnetic moment developed for the same applied field will be less. So the intensity of magnetization for the same magnetizing field intensity will be less. If the intensity of magnetization for the same magnetizing field intensity will be less, it means that the susceptibility has decreased. So on increasing the temperature of a paramagnetic substance, the susceptibility decreases. And we have got a law regarding this, that's called Curie's law. Curie's law tells us that the susceptibility of a paramagnetic substance is inversely proportional to its absolute temperature. So the susceptibility of a paramagnetic substance is inversely proportional to its absolute temperature, that is the temperature on the Kelvin scale. If we draw the graph of susceptibility versus temperature for a paramagnetic substance, it comes out to be a rectangular hyperbola because they are inversely proportional. Now let's talk about diamagnetic material. Diamagnetic materials are the substances in which we have got paired electron. So though molecule has got a net magnetic moment, and when an external magnetic field is applied within the diamagnetic substance, a field is created in the direction opposite to the applied magnetic field. So let's learn about it. Each molecule has got no magnetic dipole moment. The net magnetic dipole moment of each molecule of a diamagnetic substance is 0. When a magnetic field is applied, magnetization takes place in the direction opposite to field. So if you apply a magnetic field towards right, then a magnetic moment is developed in the material in the opposite direction. Now, if you have an applied magnetic field, understand that in case of a diamagnetic substance, a magnetic moment is created in the crystal in the direction opposite to the applied magnetic field. It means that within a diamagnetic substance, the direction of magnetic field produced due to the magnetic moment of the substance is in direction opposite to the applied. So the net magnetic field inside the diamagnetic material is less than applied. So if you have got an applied magnetic field B, the diamagnetic material will produce a magnetized field of its own in the opposite direction, B magnetized. And you will say that the net magnetic field inside in this case will be equals to the magnetic field applied minus the magnetic field due to the magnetic moment developed in the opposite direction. Now बच्चों, the diamagnetic material moves from region of stronger magnetic field to weaker magnetic field and hence repelled by a magnetic field region. You have learned that a diamagnetic material is repelled by magnetic field, right? If you take a bar magnet and move it closer to a diamagnetic substance, you know that the diamagnetic substance will be repelled. But the question is, you have to bring which pole of the bar magnet closer to the diamagnetic substance, the north or the south. The theory says that a diamagnetic substance tries to move from the region of stronger magnetic field to the region of weaker magnetic field. If you think of this bar magnet to be north-south this way, its magnetic field lines will come out of the north outside the bar magnet and they will enter into the south, right? Now nearby the bar magnet, the field strength is higher. Away from the bar magnet, the field strength is lower. So you should understand that a diamagnetic substance tries to move from the region of stronger magnetic field to the region of weaker magnetic field. Hence, it is repelled by a bar magnet. Now let's talk more about diamagnetic material. If you have got a diamagnetic material and you apply a magnetic field towards right, it develops a magnetic moment in the opposite direction. So we say that the net magnetic field inside a diamagnetic substance is less than the applied magnetic field. Now think here for a second. We know that the net magnetic field inside equals to relative permeability times the applied magnetic field. And we know that for a diamagnetic substance, the net magnetic field inside is less than the applied. This tells us that the relative permeability has to be less than 1. Then only the net magnetic field inside will come out to be less than the applied magnetic field. And we also knew that mu r equals to 1 plus psi. So we can write the susceptibility equals to 1 mu r minus 1. And if this number mu r is itself less than 1, then a number less than 1 minus 1 will give you a negative number. So do understand, for a diamagnetic substance, the susceptibility is negative and mu r comes out to be less than 1. We know that I equals to psi h, yes sir. In case of a diamagnetic substance, the intensity of magnetization is opposite to the direction of magnetizing field intensity. Hence, the susceptibility is a small negative number. Small means not large in magnitude. It can't be minus 1.2, right? It has to be a small negative number, kind of minus 0.8, minus 0.2, minus 0.3, a small but negative number. Now, if you think of the IH graph, I have just told you the slope of the IH graph gives you susceptibility. Now, for a diamagnetic substance, the susceptibility is negative. So, the slope of the graph is negative. So, a magnetic moment is developed in direction opposite to the applied magnetic field. It is no doubt proportional to the applied magnetic field, but in the opposite direction. Hence, you get a negative slope here. Next thing, bachcho, you need to understand, for a diamagnetic substance, the value of mu r, the relative permeability, is less than 1. And as mu r equals to 1 plus psi and the relative permeability is less than 1, and you know that psi is a small negative number. Now we need to talk about something called a perfect diamagnetic substance. Superconductors are said to be perfect diamagnetic substances. So the net magnetic field inside a superconductor is 0. What are you saying, sir? Yes, if you apply an external magnetic field for a superconductor, the magnetic moment developed in the opposite direction is so large that the net magnetic field inside it becomes 0. So the net magnetic field inside a superconductor is 0. A superconductor can be thought of as the best diamagnetic material. Hence can be thought of as the perfect diamagnetic substance. And bachcho, next thing. For a superconductor, you know that the net magnetic field inside is going to be 0. And we know that the net magnetic field inside equals to mu r times the magnetic field applied. Now beta, if the net magnetic field inside is going to be 0, no matter what is the strength of applied magnetic field, this means that the relative permeability for a superconductor is 0. So for a superconductor, the relative permeability is 0. And you know that the relative permeability is 1 plus psi. So 0 equals to 1 plus psi. So the susceptibility for a superconductor is minus 1. So do understand that a superconductor acts like a perfect diamagnetic substance. When placed in an external magnetic field, it develops a magnetic moment in the opposite direction which totally cancels out the external applied magnetic field. Hence, the net magnetic field inside a superconductor is zero. As the net magnetic field inside a superconductor is zero, the relative permeability is zero. As the relative permeability is zero, from mu r equals to 1 plus psi, I can say that the susceptibility for a superconductor is -1. So now it's time to talk about ferromagnetic materials. In the introduction, I said that every time you have to think of ferromagnetic material, think of a super strong paramagnetic material. A paramagnetic material is feebly attracted by a magnetic field. It tries to move from region of weaker magnetic field to stronger magnetic field. When I was a child, I was never able to understand that how come an iron block is attracted towards a bar magnet no matter which pole of the bar magnet I bring closer to the iron block. What the iron block, a ferromagnetic material, just want is to move from a region of weaker magnetic field to a region of stronger magnetic field very strongly. So think of a ferromagnetic substance to be highly paramagnetic substance. But why some substances are highly paramagnetic substances? Because they have got a region in which all the magnetic dipole align in the same direction, and these regions are called domains. So when you look in a crystal of ferromagnetic substance, do every molecule of ferromagnetic substance have a magnetic moment? Yes, like a paramagnetic substance they do, but there are small regions in which within one region all the magnetic dipoles are pointing in the same direction. And these small regions are called domains. So within one domain, all the magnetic dipole moments are aligned in the same direction. If you take a crystal of ferromagnetic substance, in the absence of magnetic field, and you have a big crystal, it will have large number of domains. And all domains will have magnetic moment in a single direction. Like this domain have got magnetic moment towards right, this domain has got magnetic moment towards left, this domain have got magnetic moment somewhere here. But the net magnetic moment of the overall crystal is going to be zero. But if you place it in an external magnetic field, the domain grows in the direction of magnetic field. So since the applied magnetic field is same as the direction of this domain, this particular domain grows and the number of magnetic dipole in the domain pointing in this direction increases. So once we have applied a magnetic field, the domain grows in the direction of the applied magnetic field, giving the substance a net magnetic moment in the direction of applied magnetic field. Moreover, some domains do turn in the direction of applied magnetic field. Like you can see in the diagram, this domain has turned as well as this domain has turned in the direction of applied magnetic field, giving us this bigger domain in the direction of applied magnetic field. So one can think of a ferromagnetic substance to be highly paramagnetic substance. Even inside a ferromagnetic substance, every single molecule has some net magnetic moment. But there are small regions which are called domains, and within a domain, all the magnetic dipole point in the same direction. Now, for ferromagnetic substance, we know that the net magnetic field inside is way greater than the applied magnetic field. So when you place a ferromagnetic substance in an external magnetic field, it develops such a large magnetic moment, which makes the field inside way greater than the applied magnetic field. This is a real world example. Let's say you have taken a ferromagnetic substance and placed it in a magnetic field of 1 Tesla. Inside the ferromagnetic substance, it is found that the magnetic field comes out to be 4500 Tesla. It means that you have applied an external magnetic field of 1 Tesla, and this crystal has magnetized so much that it has created a magnetic field of its own of 4499 Tesla. So do understand that the net magnetic field inside a ferromagnetic substance is way greater than the applied magnetic field. So mu r comes out to be greater than 1. We know that the B net inside equals to mu r times B applied. as B net inside comes out to be way greater than the applied magnetic field, it means that this mu r is a very big number. So this mu r is greater than 1, and do understand the relative permeability for ferromagnetic substances is of the order of 1000. So it is of the order of 1000. It is kind of 3000, 4000. That's how high the relative permeability of ferromagnetic substances are. And we know that the relative permeability equals to 1 plus psi. So if the relative permeability is 4000, then the susceptibility has to be 3999. So if the relative permeability is of the order of thousands, then the susceptibility is also of the order of thousands. So let's keep on talking more about ferromagnetic substances. If you look at the graph of intensity of magnetization versus the magnetizing field intensity for a ferromagnetic substances, unlike the paramagnetic substances where we get a straight line, we get a curve like this. And what is the reason for having such a curve? Reason is that when you place a ferromagnetic substance, let's say an iron bar, in an external magnetic field, as you keep on increasing the magnetizing field intensity, the intensity of magnetization keeps on increasing and then it saturates. Why is there a particular value of magnetizing field intensity above which, on increasing the magnetizing field intensity, the substance do not get magnetized anymore? The reason is that there is a certain value of magnetizing field intensity at which all the domains point in the same direction. Now, on further increasing the field strength, it can't happen that more domains are aligned in the direction of magnetic field, and then you say that the saturation is reached. So on increasing the magnetizing field intensity, the intensity of magnetization increases and then becomes constant. On increasing the applied magnetic field, the magnetization saturates as all the dipoles align in the direction of applied field, as all the domains point in the direction of applied field. We have learned that the slope of IH graph gives us the susceptibility. As here you can see the slope keeps on changing. We say that for a ferromagnetic substance, the susceptibility keeps on changing with the magnetizing field intensity. So the susceptibility of ferromagnetic substance changes with the applied magnetic field. Now, talking more about ferromagnetic substance. On increasing the temperature of a ferromagnetic substance, the susceptibility decreases. And here we need to talk about one important thing, that is called Curie's temperature. So what exactly is Curie's temperature? The Curie temperature is the temperature at which the domains break. And once the domains break, now the ferromagnetic substance acts like an ordinary paramagnetic substance. So let's say the Curie temperature for a particular material is 500 degrees centigrade. It means that below 500 degrees centigrade, it will show ferromagnetic nature. But above 500 degrees centigrade, it will act just like a paramagnetic substance. So the temperature at which the domains break, and above the Curie temperature, the thermal agitation is so large that you can't have domains. So the ferromagnetic substance ends up acting like a normal paramagnetic substance. And above which ferromagnetic substance acts like a paramagnetic substance. For the temperature above Curie temperature, we have got a law just like Curie's law for paramagnetic substance. For paramagnetic substance, we said that the susceptibility is inversely proportional to the temperature on the Kelvin scale. But we know that the ferromagnetic substance acts like a paramagnetic substance only above the Curie temperature. So we say that the susceptibility of a ferromagnetic substance above Curie temperature is inversely proportional to the temperature above the Curie temperature. So the susceptibility is inversely proportional to the temperature above the Curie temperature, because only above the Curie temperature a substance acts like a paramagnetic substance. Now this particular law is called Curie-Weiss law. Moving on now to comparison of paramagnetic, ferromagnetic, diamagnetic substances together. So let's get them here. First of all, let's talk about paramagnetic substance. In the case of paramagnetic substance, the magnetic moment of each molecule is non-zero. In case of diamagnetic substance, the magnetic moment of each molecule in the absence of external magnetic field is zero. And in case of ferromagnetic substances, again, the net magnetic moment of each molecule is non-zero, just like that of paramagnetic. If you look at the value of susceptibility, for paramagnetic substances, the susceptibility is a small positive number. For diamagnetic substances, it is a negative number, but the magnitude is less than 1. And for ferromagnetic substances, susceptibility is large, of the order of 1000. If we talk about relative permeability, we know that inside a paramagnetic substance, the magnetic field is more than applied magnetic field. Hence, the relative permeability is greater than 1. For a diamagnetic substances, we have learned that the permeability comes out to be less than 1. And for superconductors, which are perfectly diamagnetic substance, the relative permeability is 0. So for diamagnetic substance, the relative permeability lies somewhere between 0 and 1. And for ferromagnetic substances, again the relative permeability is a large number of the order of thousands. Now let's talk about the intensity of magnetization versus the magnetizing field intensity graph. For paramagnetic substance, you get a straight line, the susceptibility is constant and the susceptibility is positive. For diamagnetic substance, you get again a straight line, but you can see that the slope of this straight line is negative because the susceptibility is negative. And for ferromagnetic substances, the susceptibility keeps on changing with the value of magnetizing field intensity as the slope keeps on changing. One more thing, for paramagnetic substances, we have learned the Curie's law that the susceptibility is inversely proportional to the temperature in Kelvin. And for ferromagnetic substances, we know that the susceptibility is inversely proportional to the temperature above the Curie temperature. So above Curie temperature, a ferromagnetic substance acts like a paramagnetic substance and its susceptibility is inversely proportional to the temperature above the Curie's temperature. So now we will talk about the hysteresis graph. What is magnetic hysteresis? You have the fan in your house, yes. Which metal do you think fan contains the most? It has got winding that is made up of copper, yeah. And I think that fan is also made up of iron or steel, right? Now many and electrical appliances that we use have got the presence of ferromagnetic substances in them. And the type of current supply we use in our household is AC current supply, alternating current supply. And that's why understanding hysteresis becomes important. What is hysteresis, sir? Let's understand it one by one. Assume that you have a solenoid and this solenoid is connected to AC supply. What is the difference between AC and DC? In DC, the direction of current is constant. In AC, the direction of current keeps flip-flopping. You have seen this graph of the current versus time for an AC, right? So the current first increases in the positive direction, becomes maximum positive in one direction, then drops to 0, then start increasing in the opposite direction, becomes maximum negative possible in opposite direction, then again drops to 0, and then becomes positive in the same direction, reaches the maximum value, then drops to 0, and this cycle keeps on continuing. If you connect a solenoid with an AC supply, what happens to the direction of magnetic field inside the solenoid? So sir, first, as the current will increase, the magnetic field will increase in one direction. And then as the current will decrease, the magnetic field will decrease in that direction. So first increase in one direction, then decrease in that direction. Then the current starts increasing in the opposite direction. So the magnetic field starts increasing in the opposite direction, then decreasing in the opposite direction, then increasing in one direction, decreasing in one direction, then increasing in opposite direction, decreasing in opposite direction. And this is how the magnetic field keeps on varying inside the solenoid. As a matter of fact, all the devices which we use operate on AC. And in AC supply, the direction of current keeps on fluctuating. So the direction of magnetic field produced by them keeps on fluctuating, increases in one direction, decreases in that direction, increases in opposite direction, decreases in that direction, and this keeps on happening. The frequency of the AC supplied in our household is 50 Hertz. It means that 50 cycles per second. It means that 50 times every second, the field strength increases in one direction, decreases, then increases in opposite direction, then decreases. And this is one cycle. And it happens 50 times in 1 second. So that's the frequency. Now, what happens when the magnetic field intensity increases in one direction? And we are talking about ferromagnetic substances. So as the direction and magnitude of current keeps on changing, so is the direction and magnitude of magnetic field, right? As the direction and magnitude of current keeps on changing, so is the direction and magnitude of the magnetic field. It increases in one direction, decreases in that direction, increases in opposite direction, then decreases in the opposite direction. If we look at the intensity of magnetization versus the magnetizing field intensity graph, what does the graph looks like? First, let's think of from zero magnetic field, the magnetic field increases in one direction. When the magnetic field intensity increases in one direction, we say that the intensity of magnetization increases in that direction. And we know that what does the IH curve looks for such a case? The IH curve for such a case is nothing but this. So as the magnetizing field intensity increases, the intensity of magnetization increases. Now the game starts. Now as the magnetic field intensity starts dropping from the maximum and becomes zero, the intensity of magnetization also starts decreasing but do not become zero. This is called the memory of the ferromagnetic substance. Even when the magnetizing field intensity in one direction has reached maximum and then dropped to zero, the intensity of magnetization do not drop to zero. And this residual magnetization, even when the magnetizing field intensity has become zero, is called retentivity. How much magnetization the substance retains even when the external applied magnetic field has dropped to zero. Now when the magnetic field starts to increase in the opposite direction, the ferromagnetic substance starts magnetizing in the opposite direction. So as the magnetizing field intensity starts increasing in the negative direction, the intensity of magnetization first drops from some value which was called retentivity to zero. This particular value of magnetizing field intensity that has to be applied in the opposite direction, so as to completely demagnetize the substance so that the intensity of magnetization becomes zero, is called coercivity. Then the field keeps on increasing in the opposite direction. So the whole ferromagnetic substance starts magnetizing in the opposite direction and reaches a maximum in opposite direction. Then the field starts decreasing in the magnitude in the opposite direction. When the field starts decreasing in magnitude in the opposite direction, the intensity of magnetization also starts decreasing in the opposite direction. But when the field in opposite direction becomes zero, still some magnetization persists in the opposite direction, in the negative direction. Again, this intensity of magnetization that is found in the negative direction, even when the magnetizing field intensity has dropped to zero, is again called retentivity. Now the field again starts increasing in the forward direction. First, the intensity of magnetization, which still points in the backward direction, drops to zero. And then on further increasing the field in the positive direction, it again saturates. And this particular graph is called the hysteresis curve. Now here we should know about these points A, B, C and D. Here बच्चों point A and C represents the retentivity of the material. Retentivity, also called remanence, is the intensity of magnetization that persists even when magnetizing field intensity has dropped to zero. So we say that A and C represents retentivity, while B and D represents coercivity. Now let's understand these terms once more because they are important. So hysteresis means what? Do understand the intensity of magnetization, how much the crystal has been magnetized, lags behind the magnetizing field intensity, the field which is trying to magnetize the substance. So if you think of the IH curve, with the increase in H, I increases. When the H drops to zero, the I still persists, and this particular point is called retentivity. When the H starts increasing in the negative direction, I then drops to zero. When H further increases in the negative direction, the crystal saturates in the negative direction. Then when the magnitude of H decreases in the negative direction, I decreases in the negative direction, but still some magnetization remains even when H drops to 0. Then when H again increases in the positive direction, I drops to 0. And with further increase in H in the positive direction, this crystal again saturates. So beta, the point A and C here represents retentivity. The point B and D here represents coercivity. So let's understand what is the meaning of retentivity. The residual intensity of magnetization when the magnetizing field intensity drops to 0 is called retentivity. Once more, the residual intensity of magnetization when the magnetizing field intensity drops to 0 is called retentivity. And what is coercivity? Coercivity is the magnetizing field intensity to be applied in the opposite direction to demagnetize the substance is called coercivity. Once more, the magnetizing field intensity to be applied in the opposite direction to demagnetize the substance is called coercivity. So you need to know these terms. We even need to know that the area enclosed within the hysteresis loop represents the energy loss per unit volume of the crystal per cycle. So remember that the area enclosed by the hysteresis loop represent the energy loss in this flipping flopping of domains per unit volume of the crystal per cycle. So greater the area of the hysteresis loop, more is the energy loss, less is the area of the hysteresis loop, less is the energy loss. So the last thing left out here to discuss in this hour is the difference between hard magnetic material and soft magnetic material. So let's do it. So let's talk about soft magnetic material and hard magnetic material. When we say that soft magnetic material, it doesn't mean that the material is soft. When we say soft magnetic material, it means that the material can be magnetized or demagnetized easily. And when we say hard magnetic material, it means that the material is difficult to magnetize, and if once magnetized, it is difficult to demagnetize. Yeah, it is kind of inertia. A soft magnetic material can be both magnetized easily as well as demagnetized easily, while the hard magnetic material is tough to magnetize, and once magnetized, it is difficult to demagnetize it. So, a soft magnetic material has low coercivity, so it can be demagnetized easily, can be magnetized and demagnetized easily. And the hard magnetic material has a high coercivity, so once magnetized, it is difficult to demagnetize it, can't be magnetized as well as demagnetized easily. Now, if we look at the IH graph of soft magnetic material and hard magnetic material. For soft magnetic material, the coercivity and retentivity both have got smaller value. So the area enclosed by the graph is small. For hard magnetic material, the coercivity and retentivity both are large. So the area enclosed by the graph is more. So you will say that as it has got smaller area enclosed within the hysteresis loop, so less energy loss per unit volume per cycle, and as it has got more energy enclosed within the hysteresis loop, there is more energy loss per unit volume per cycle. Now comes the most important part from where the question will be asked on soft magnetic material and hard magnetic material, their usages. You need to understand that the type of supply in our household is AC, and ACs are stepped up or stepped down using transformers. If within the transformer you will use a hard magnetic material, then there will be more energy loss per unit volume per cycle, and we don't want that. We want less energy loss. We want our devices to be more efficient. So remember that in the core of the transformer we use soft magnetic material and not the hard magnetic material. So you will say used in the core of transformers and to make electromagnets. Have you ever heard of the usage of electromagnet? Let me tell you one usage which is used for doorbells. We take a solenoid, okay, we wrap a wire around it, and then we put an iron piece within the solenoid, and this iron piece is connected to a spring. And here we have placed a gong, an iron gong. When we drive the current in the solenoid by pressing the bell, As the current drives through the solenoid, a magnetic field is developed. This is a ferromagnetic substance inside the solenoid. So it gets magnetized very easily. Once it gets magnetized, it is attracted towards this iron gong and it goes and hits it. Once it hits, we get the sound of ting tong. And then this circuit, when broken, once you have taken the finger off the switch, this iron piece is retracted back because of the spring attached. Now tell me if this iron piece will be made up of hard magnetic material. Even on turning the current off, it won't get demagnetized easily. Once magnetized, it will act like a permanent magnet and it won't leave the gong. But you want the iron piece within the solenoid to go hit the gong, and once the current stops, to come back, right? So that's why the type of material used within the electromagnet is of soft magnetic material. Electromagnets are the substances which we need to act like a magnet only when current is flown through the circuit. We want it not to act like a magnet when no current is flowing. So in electromagnets, we use soft magnetic material. And sir, where do we use hard magnetic material? To make permanent magnets. If you have a permanent magnet in your house, which can be demagnetized easily using any current flowing in the house, that won't be a good magnet. You want a permanent magnet to have high coercivity, so it can't be demagnetized easily. So remember that hard magnetic materials are used for making permanent magnets. So that's all in this hour. See you guys in next hour, where we will start the topic of electromagnetic induction. That's a really lovely topic. See you guys in next hour. Bye bye. So that's all for now. See you guys in the next hour.